This lesson, this video lesson, deals with the second gas law that we're looking at in our series of gas laws, and that is Charles' gas law, which volume. Right off the bat, we're going to start with a animation to show you on the volume a cylinder that has variable walls. And in this case, we have a that can move forward, maintains a constant pressure, and I've reduced the temperature in the model to 100 Kelvin. And we can see that after given some time, the piston moves to a lower volume. And in a second, what we're going to do is stop it and reset the pressure, or the temperature, sorry, to a higher temperature, 500 Kelvin. Now remember, the volume here is changing, but the pressure is not. So this piston will move so that it bounces out to equal the pressure. We know that with increased temperature means that the particles move faster. And if particles are moving faster, they want to take up more space and create more space between them. And so as we can see that every time we increase the temperature and we run the simulation, the volume is a way to at a constant pressure is to increase the volume, because the particles now are hitting the piston with much stronger, and because of that, the collisions are stronger and they would be applying pressure to that. So what we're going to do right now is take a quick look at Charles' law, the relationship between temperature and volume, and attempt to identify mathematically what that relationship is. So first of all, let's identify the type of relationship, because this one is different than Boyle's. In the case of Boyle's relationship, we had an inverse relationship. The two variables were inversely proportional, pressure and volume. If one went up, the other one went down. In this case, as we can see here, when we increase the temperature, the volume also increases as well. So these two variables are directly proportional. So we have directly proportional variables here. As one increases, the other one increases as well. What I've done here is I've shown you a graph of three different gases, gas A, B, and C. And with experiments done starting at 0 degrees Celsius, it was noted that there was always an initial volume, even at 0 degrees Celsius. And as the temperature increased, so did the pressure. Interestingly enough, we can extrapolate backwards along the lines, and it turns out that all three graphs meet at the exact same point. And this temperature right here is minus 273.15 degrees Celsius. And it turns out that all ideal gases will reach what we would call a hypothetical point where there's absolutely no volume. Although later on when you take chemistry, you'll learn that that is impossible to actually reach this point. Theoretically it's there, but we can't reach it. We call this point absolute zero. So that's the smallest temperature that anything can have, but at that point any gas has absolutely no volume. And so scientists had to develop a new temperature system. So this point, what we call absolute zero, what that refers to is the new temperature, that is 0 Kelvin. And so when it comes to gases, we need to use a new temperature scale, and that's the Kelvin scale. And to determine a temperature in Kelvin, say we had 20 degrees Celsius, and we wanted to find out what that was in Kelvin. So what we would do is we would take our 20 and we would add 273 to it. We won't worry about the 0.15. And we get 293 Kelvin. So anytime you want to determine a temperature in Kelvin, you would just take the temperature in degrees Celsius and add 273. If you want to go backwards and figure out your temperature in degrees Celsius, you would just take your Kelvin and you would subtract 273 from it. Pretty straightforward. But what this temperature of Kelvin, this unit of temperature allows us to do is to get the correct mathematical relationship between temperature and volume, and then later on temperature and pressure. So what we're going to do is we're going to use these graphs to determine what the mathematical relationship is. And because we have linear relationships, we're going to use y equals mx plus b. Now our b, because we do reach the 0 point, is going to be 0, because our y-intercept is 0. And our m is the slope, and the slope is not changing along the line. So because it's not changing, we're going to say it's constant. It's going to be very important because we'll solve for m to determine what the relationship, mathematical relationship is between volume and temperature. So we're going to sub in our variables, v and t. So our y is v for volume, and our x is t for temperature. And we don't have to worry about b because it's 0. So now let's get m by itself. So we'll divide by t, and we get v over t equals m. And because this m is constant, it doesn't matter where along the line we go, the relationship between volume and temperature will always be the same. So we can express that as v1 over t1 is equal to v2 over t2. Now remember, it's directly proportional relationship. So if v increases, then t must also increase. And if we look, because we're dealing with a we're dealing with a fraction, a ratio that's a fraction, in order to make sure that this is equal to that, any change that happens up here must be met down there in order to keep this ratio here the same as that ratio. So what we're going to do now is we're going to apply this relationship to a question. So we've got a problem here. We've got a balloon. It's inflated with air in a room in which the temperature is 295 Kelvin. It has a volume. The balloon is put into a refrigerator at 277 Kelvin. It's left long enough for the air in the balloon to reach the same temperature as that in the refrigerator. Predict the volume change and the air pressure in the room and the refrigerator is the same, which doesn't always work. But in this case it should work. Now, even though temperatures have to be in Kelvin, it doesn't change to liters right now. So our total volume is 650 milliliters. Our Kelvin temperature is 2 Kelvin. Now before we go anywhere, what should happen here? We want to solve volume, but we need to look at what's happening with our temperature. T2. T2 is smaller. So because of this, because temperature have a direct relationship, if my pressure, so my temperature ends up going, therefore my pressure must also go down. So here our V1 must be greater than our, we always do these little quick minutes before we approach the question. You know, when we develop our formula or plug our numbers in, we can quickly check back if we got what looks like to be the correct answer. Well, we over T1 to V2 over T2. Now, so what we're going to do is we're going to add the T2 up. So V2 to V1 times 2 T1. So now we is equal to V1 initial volume is 50 milliliters. Temperature is 277 Kelvin. Add that by our initial temperature, which is 295 Kelvin, times 275 equals 110 mil. So there we go, and our temperature too much by 18 Kelvin. So our volume is not going to decrease massive amount. What questions? Pause it. Write the questions out and attempt them right now, and then I'll show you the answers and you can make sure that you've done this correctly. Okay, in this first question we have a birthday balloon again. It's filled with the said volume, 1.5 liters helium, and an air-conditioned room at 294 Kelvin. The balloon's taken outdoors on a sunny day and left to float as a decoration. The volume of the balloon expands to 1.55 liters. So we're making a big assumption here that the pressure outside is the same as the pressure inside. But no big deal. So it's just a theoretical question. So let's pull back the curtain and see what we get. So initially, I write down what information we're given. Always do this. What are we given? Then how are we going to find our answer? In this case, we want to find what the temperature is of the gas after it's expanded. And there we go. We initially find our final temperature in Kelvin. It obviously went up. If the volume expanded, then the temperature is going to have to increase. And then to get my temperature in degrees Celsius, I just take my temperature in Kelvin, subtract 273, and there you go. And this next question, we've got the temperature of a sample of gas is going to decrease from 35 to 20 degrees Celsius. So obviously our volume is going to have to decrease as well. But again, we start out by writing down what we know. This one's a little trickier because our temperature is given in degrees Celsius, so we have to convert the two temperatures into Kelvin. but we know it is decreasing, so we should get our volume gain smaller. Identify the relationship, then identify the equation that will solve for our answer. And there we go. V2 is 2.25 liters times 293 Kelvin over 308 Kelvin, and we get 2.14 liters, which is less than our initial volume. So there we go. This concludes the section on Charles's law and the relationship between temperature and volume of ideal gases.